Today we are going to discuss rigid body rotation under classical mechanics. In particular, we will be discussing moment of inertia tensor, principal axis, and the Euler's equation for rigid body rotation. So let's get started. So here this is a picture of a body rotating about an axis with frequency omega, and we have this so we have this axis, we have this coordinate system xyz which is fixed in space, and the axis of rotation is here. So this is the axis of rotation. So this passes through a point O, which we refer to as the origin. So this is the xyz coordinate system fixed in space, and this is the body that is rotating in space about, say, some axis omega. So we consider here infinitesimal mass situated at radius vector r from the origin. So here we have this. So this is my infinitesimal mass located at a radius vector r. So if that is the case, then the angular momentum for this mass is actually dl vector is equal to r cross dp vector. dp vector is the linear momentum of the mass. And what is dp vector? dp vector is nothing but dm into v vector. V is the velocity at that point, velocity vector. And if it's rotating with a frequency omega, then v can be written as omega cross r. So this is dm r cross omega cross r. So my L vector will be, if you just integrate, will be integration dm then r cross omega cross r. So this thing, if you do the calculations, then if you complete the algebra, which we will not do it here, this is L vector is I tilde into omega vector. So this is L vector. So L vector is here is a column vector, and omega is also a column vector, and I tilde is it should be it should be I. So this should be this should be I tilde is the moment of inertia tensor. This is the moment of inertia tensor. So how does it look like? This moment of inertia tensor looks like this. So integral y square plus z square dm xy. So integral is over mass. So this you can convert it into space. So you can write, so dm is okay. So dm is equivalent to rho, if we are integrating over three-dimensional space, rho, and then we have dx dy dz. dx dy dz. dx dy dz. Sorry. Okay. Or if you're dealing with if you're integrating a two-dimensional space, then rho will be like this is density of mass. You can just areal density. Rho can be substitute by sigma. Sigma dx dy is like that. Okay, so dm, so this thing can be written by this, and this is what it. Okay, so we can do a so if we go to a coordinate system, so we were working in this coordinate system, so and we obtained this inertial moment of inertia tensor. So if we are working in a coordinate system in which this moment of inertia tensor is diagonal, then that coordinate system consists of the principal axis of the system, and the moment of inertia along those principal axis is given by I1, then you have I2, and then you have I3. So the importance here is that you can see the moment of inertia tensor. That means in this particular case, the moment of inertia, say along x-axis, not only depends upon the angular frequency, the frequency component along x-axis, it also depends on the angular momentum along x direction. Here depends not only on the angular frequency along x direction, but it also depends on the angular frequency along the y direction, and that is along this y direction. What is the angular frequency? That is omega y, and it also depends on omega z in general. But if you are working in the principal axis coordinate system, then for the same problem, the angular momentum, say along one direction, this direction, will only depend on the angular frequency component along one direction, and it will not depend on omega 2 or omega 3. So that is the advantage, and we are going to use this extensively in rigid body rotation, this property. So that's why this moment of inertia tensor is important, because it gives us the principal axis and the eigenvalues I1, I2 and I3. These are the eigenvalues. So let us do a simple problem. So here we have to calculate the moment of inertia tensor of a square plate about an axis passing through the origin. So see figure in the next page. So this is my figure. So this is my x, y, z. So there is a plate in the xz plane, is a square plate, and we have to find the moment of inertia about any axis that passes through the origin O. Okay, so it passes through the origin O. Anything that passes through any axis, arbitrary axis that passes through the origin O. And if we use this expression, we immediately get my expression. My I tensor is this you can calculate, ms square by 3. These are the entries of the moment of inertia tensor. Okay, sorry, I think there will be minus ms square by 4, then I think there will be this is, so if this is a minus, then there should be a minus here also. Okay, so this is my tensor. This you have to just check, because there is there is a minus here, so there will be a minus. So the eigenvalue equation is I omega is equal to I omega. If this is so, if this eigenvalue has to be correct, the eigenvalue equation has to hold, then the eigenvalues have to be this 2ms square by 3, I2 will be 7ms square by 12, and I3 will be ms square by 12. And for each of this eigenvalue, the principal axis here in this case for L1, I1, it will be j cap, that is the principal axis will be along this direction for this eigenvalue. And for I2, so we have given here the unit vectors. For I2 it will be, you can say the unit vector will be this, 1 by root 2 I minus k cap. And for m square by 12 I3, the principal axis will be given by 1 by root 2 I plus k. So I plus k you can easily see will be in this direction, somewhere along this direction. Okay, along this direction. Similarly, you can find out what will be the direction of I minus k 1 by root 2. Okay, so this is how you do it. Similarly, you can do another problem. Find the moment of inertia tensor for a square plate as shown in the figure in the next page. Hence, find the principal axis for the system and the corresponding eigenvalues. So, this is the figure. So, this is the square plate in the xz plane. Now, this is the axis. We take any arbitrary axis that is passing through the center of the plate. So, the axis will pass through this point. And this is a square plate. So, for this geometry, if you calculate the moment of inertia tensor, you can find these are the entries. It is basically a diagonal matrix. And if it's a diagonal matrix, that means what are the eigenvalues? The eigenvalues are obvious. And what are the eigenvectors? So here the eigenvectors are also very obvious. So the coordinate system that we started with, they form the eigenvectors here. And here the eigenvectors were given by these: j cap, 1 by root 2 I cap minus k cap, and 1 by root 2 I cap plus k cap. So now we go to Euler's equation. So we are now considering a body that is rotating in rigid body that is rotating in space. So we are now going to the coordinate system that is non-inertial. So because calculations will be easy. So we know that the time derivative in an inertial frame of any observable is related to the time derivative of the observable in a rotating frame through this relation. So this is the relation that connects the time derivative of an observable in the inertial frame to a time derivative of an observable that is in a that is being observed in a rotating frame, and that frame say is rotating with an angular frequency omega. So here I can put omega vector here, that I forgot. So omega vector. So omega vector here. So if our interest lies in the angular momentum L vector, then we put L vector here. If that is the case, so dl dt is nothing but the torque, and in this case we write L as I omega, and here is the moment of inertia tensor, and now we are in a rotating frame, a frame that is rotating along with the body. If that is the case, then I is a constant. Okay, so here in this rotating frame, what happens is I is constant. I is constant. Okay, I is constant. This is a constant. This is a that. This is a constant. This is a constant. And so it actually comes out of this derivative sign, and we are left with only d omega dt. Not only is a constant, if we choose our axis as a principal axis, okay, then not only it becomes a constant, then at the same time this thing also becomes diagonal if we choose our coordinate system as the principal axis. So this is the principal axis coordinate system. Okay, so we are not only is the coordinate system rotating along with the body, it's also principal axis coordinate system. So if that is the case, then your eye this is diagonal. It also becomes diagonal. Okay, so this becomes diagonal. Change my stylus. Okay, this becomes diagonal. This becomes diagonal. If that is the case, then equations simplify, and what we get from here is the Euler's equation. So these are the very important equations for rigid body rotation. So these are the torques along direction 1, this is the torque along direction 2, and this is the torque along direction 3, and that is related to I1 moment of inertia along direction 1 into omega 1 dot, I2 minus I3 omega 2 omega 3. So other equations are also similar. So we have three equations which describe the rigid body rotation, and these are the Euler's equation. So Euler's equation can be, so we will just give an example of how things can be solved using Euler's equation. So here we have a rigid body spinning in a torque-free region, okay, with its moment of inertia along the principal axis, related as I1 is equal to I2. So it's kind of a symmetrical top where I1 is equal to I2 and I1 is equal to I2 not equal to I3. Show that the body can only spin with an angular frequency of magnitude, constant magnitude. So what we have to prove, that the frequency of rotation of this rigid body is constant in magnitude if this condition holds. That is, the magnitude does not change with time. If I1 is equal to I2 is not equal to I3. If this condition holds, then it can only spin with an angular frequency of constant magnitude. So we go back to this Euler's equation, and immediately we see that if I1 is equal to I2, then, and we are working in a torque-free region, so no torque, so 0. So last equation is I3 omega 3 dot is equal to 0. That means omega 3 is a constant, and let us call it capital omega. So this is the component of the rotation along direction 3. So we are left with two other directions. So in both we have omega 3. So there we replace omega 3 by capital omega. Okay. And as soon as we do that, we can easily see we can, from this and this equation, we can write omega 1 double dot is equal to I1 minus I3 whole square omega square divided by I1 square into omega 1 is equal to 0. Just you have to just take a double derivative here. So we have omega 1 double dot, we have omega 2 dot, and then replace omega 2 dot from this relation, and you will get this relation. So this is the equation of a simple harmonic motion. So omega 1 satisfies simple harmonic motion. Similarly with omega 2 double dot satisfies a similar simple harmonic motion. L1 minus L3 omega I1 minus I3 omega square capital Omega square divided by I1 square omega 2 is equal to 0. If that is the case, then I can. So it basically tells us that the omega 1 changes with the frequency, and that frequency is alpha, and that is I3 minus I1 into omega divided by I1. So omega 1 changes with this frequency. That is, I can write my solution for omega 1 as some omega naught sine alpha t, and my expression for solution for omega 2 is omega naught cos alpha t. If we assume that at time t is equal to 0, omega 1 was 0, that is the component of angular frequency along direction 1 was 0, okay, and the component of the component of omega 2 and the component along 2, that is omega 2, was omega naught. And from here we can see that the magnitude of the total spin angular frequency is omega naught square plus omega square square root. Okay. So from here we can see one thing. So this is the body, and this is direction 1 principal axis, which is rotating with the body. This is omega 2, and this is direction 2, and this is direction 3. So this angular frequency has a constant component omega along this direction, and this omega 1 is changing according to this relation, omega naught sine alpha t, and omega 2 is changing according to this relation. So basically, what is happening is that if this is my angular frequency, which is a vector, then what is happening is that this is precessing. So this is going around with an angular frequency alpha. Okay, so this is going around with an angular frequency alpha, and so that is the thing. So it is going. So the angular frequency is going around this direction 3 with an angular frequency alpha, and that is why we have this omega 1 and omega 2 changing with time. Okay, so this is the precession motion of a rigid body in a torque free region, satisfying this condition: I1 is equal to I2 not equal to I3. And so we see that this is a constant. This is independent of time, this thing. So this is my omega naught. It's the projection of this angular frequency on the 1-2 plane is omega naught. So omega naught square plus omega square is my total. Square root of that is my total angular frequency magnitude, which is independent of time. We now go to the last problem. So this is, we refer to what is the problem of gyroscope. So this is a disc axle system, is mounted at O, and the disc is made to spin about an axle with angular frequency omega. The disc axle system is free to rotate about O with frequency omega, as shown in the figure. Show that the relation between the precession frequency capital omega and this omega is equal to 2gd divided by r square omega, where d being the distance between the axle and disc and r is the radius of the disc. So this is the figure. So this is the disc. This is the disc which is rotating. It is mounted at O with the help of an axle. So the disc is rotating about the axle with a frequency omega, and if it is free to rotate, it's going to rotate. It will rotate with an angular frequency omega. So this is the precession motion. So this is the axis of rotation, and the axis of rotation will also rotate about this point O. So we have to find out the relation between this omega and the small capital omega and the small omega. So this happens because so there is a torque acting on the system, and that is causing all this motion. So the magnitude of the torque is mjd, and if you consider the direction of the torque is r cross f. Okay, so this is my the force is the weight mg, and r is in this direction. Okay, so r is in this direction. R cross f means the torque is acting into the page. So this torque is causing the rotational motion. So how? So torque is equal to mgd, and that is nothing. Torque is nothing but rate of change of angular momentum, magnitude. So we can write this thing as dl vector is equal to mg dt. And what is dl vector? Now we can write this dl vector as, so this is my, say, L vector. Okay, so after time dt it becomes L plus dl. This is L plus dl. This is my L vector. Okay, this is my L vector, and this is my dl vector. This is the dl vector, and this is my angle phi. This is my angle d phi. So this is the thing I am looking at from the top. This picture I am looking from the top. So this is what I see. Okay, so dl is L into d phi, dl magnitude, and that is what we get. So once we write L into d phi is mg dt, then d phi dt is actually my, so what is this? So d phi dt is my capital omega. D phi dt is my capital omega. So you can now complete it. So what, but there is one important assumption here. So what we have written here that this L is mainly due to this frequency of rotation about the axle. We have not considered so what we have done is we are ignoring the angular momentum due to the precession omega. Why we are ignoring? Because we are considering a situation where omega is much greater than capital omega. If that is the case, then this L is almost equal to, L is approximately equal to I omega. And once we write it is equal to I omega, then we will get the relation that we are looking for. Noting the fact that the moment of inertia of a disk about its center is half mr square. Okay, so this you can complete. So we'll end here, and in the next lecture we will continue with another topic of classical mechanics, and sometime we will do also Euler's angle. So thank you.